Hello everyone, this is Lian Marie Barangco of PSEC 3C, and for EC23 or Communications 2, in performance task number 7, we are going to solve the given binary codes by using the Hamming 12-8 coding scheme. Hamming code is a set of error correction codes that can be used to detect and correct the errors that can occur during transmission of data. In this video, we're going to use the 12-8 coding scheme, and it is easy to understand once we start to answer the given problems. So first, this is the Hamming table, where the bit position is labeled 1 to 12. In our case, since we're using the 12-8 coding scheme, so the bit position is from right to left. And the given bits are going to be placed according to the respective pattern in our table in the encoded bits, where the X are going to be replaced by 1 and the blanks are going to be replaced by 0. And solving by Hamming matrix. So we have here the given letter L, and B, which we converted to its ASCII code, 8-bit ASCII code. We're going to use this. So for our first code, or code 1, which is 010011000100, we're going to multiply it to the encoded value from our table. So the equivalent of our table in here, which is 0011, and respectively is seen in this matrix. So in finding the four unknown values, we need to multiply D8 to this first set of numbers, and then D7 to the following, D6, D5, and P4, which means the fourth parity, and so on. So in code 1, we're going to multiply the following values of the code according to its chronological arrangement to the set of the numbers. And since we have here the following values of 0, which means that the product would be equal to 0. So we're going to disregard the set of numbers that is going to be multiplied by 0. So we only keep the values which is multiplied by 1. So we can determine the final answer. So here, 1 times 1, 1. This is 0, and then 1 times 1, another 1, and lastly 1 times 1, 1, which is equals to 3. And for the second unknown value, 1, 0 again, and then 1, and lastly 1, which is also equal to 3. And the next one is, this is 0, 0, 1, and then 0. So we only have value of 1 in unknown number 3. And for the last unknown is 1, 1, that's it. So it's equals to 2. And if it is even, if the answer is even, then in our coding it is going to be equal to 0. And if it is odd number, it is going to be 1. So 3, 3, and 1 are odd numbers, and 2 is the only even number. So we have here their value, which is 1110. And it means that we have an error in our coding. And the error is here, the 1110, its equivalent, which is the first, second, third, fourth, fifth, sixth, seventh, the 7th bit number. So the error is at bit number 7 and its given value is 1. To correct it, we change this given value into 0. And now instead of our original data, which is 01001 10000100, the corrected value will become 010010000100. Okay, so in our code 1, this is the final answer. And this is the hexadecimal equivalent of this binary data. Okay, next, we're going to solve another example of code 2. The code 2 is the continuation from our given data. So our code 2 is 110001000010. Again, we're going to base on our given table to find the matrix that we're going to multiply with this data. It is still the same because this coding scheme is 12-8. Just like before, we're going to multiply them and then disregard the set of numbers that will be going to be multiplied to 0 since their product is automatically 0. So first, 0, so 1, which is equals to 2. And for the second unknown value, 1, and 1 equals to 3. For the next value, 1 and then 1 equals to 2. And lastly, 1 and 1 equals to 2. Again, if the value is even, it is going to be 0, and if it is odd, it will be 1. So our value is 0100, which is equivalent to this. The second bit means that the parity 2 or P2 is error. There's an error. So the error is in bit number 2. Its given value is 1. To correct it, we change it into 0. So instead of having our original data, which is 110001000010, it will become 110001000000 as the corrected value. So this is the final answer for the second code from our given data. And also, this is the hexadecimal equivalent of the binary numbers. And for the summary, if the answers are all zeros, it means there's no error in our data. In determining the check bits or parity bits, we use even parity, where we convert the value to 0 if it's even and 1 if it's odd. And the general rule in Hamming codes is numbering the bits starting from 1 with the direction from right to left. And we used Hamming 12-8 in the given problems, but Hamming 7-4 is more common. And there are also codings such as Hamming 15-11 and 21-16. That's all. Thank you.